In this lesson we're going to continue to look at the half-life of radioactive materials. Now, as with the previous lesson, we're going to start off with our imaginary sample of radioactive isotopes, and that at time t equals 0 none of those isotopes had decayed. And then we symbolically, using this pictogram, represented the decays of the isotopes after time periods of t, that's to say after one half-life, and then after another half-life, and then after another half-life. And we noted that the number of remaining radioactive isotopes dropped by 1/2 after each half-life. Again, I must stress that these are pictograms. In our representation, the isotopes that have decayed, that's to say these red atoms, should be completely randomly distributed throughout the sample. They're not organized in this neat little way. That's just to help us understand what's going on. So in reality they should be randomly distributed throughout each sample. Now then, what we mentioned at the end of the lesson was that it's really quite impractical to measure the number of decayed isotopes present in a sample. What is much more practical is to measure the rate at which the isotopes are decaying, or what we call the count rate. And the key point that we should see here is this. Firstly, that the probability or the chance of any of these radioactive isotopes decaying at any moment is directly proportional to the number of radioactive isotopes present at that moment. So if the chance of a decay is proportional to the number of radioactive isotopes present, then the rate of decay of those isotopes is also directly proportional to the number of radioactive isotopes present. So if after one half-life the number of radioactive isotopes present drops by 1/2, then the probability or chance of one of these isotopes decaying has also dropped by 1/2. Therefore, the rate at which these isotopes will decay will also drop by 1/2. Likewise, if we move on by one half-life, the probability of any of these radioactive isotopes decaying will also drop by 1/2, and the rate at which they decay will therefore drop by 1/2 too. Let's just attach some figures to this to help make it clearer. Let's just say, for the sake of argument, that in our imaginary sample here we measure the decay rate. To do that, we're going to use a Geiger-Müller tube or a Geiger counter. Okay, so we've got our radioactive source, our radioactive sample here, and the Geiger counter is going to measure the rate at which it is decaying. Let's just say, for the sake of argument, that we find that the decay rate of this sample is 80 counts per minute when we start the experiment. In fact, I'm going to abbreviate that to give myself more space. So we'll write it as 80C per minute. Okay. Now then, we move on by one half-life. Now that half-life might be 10 minutes, or it could be a couple of hours, or it could be a day. It really doesn't matter. What is important is we advance by one half-life, and then we turn our Geiger counter on and we find that the decay rate is now 1/2 of what it was when we started. So it will now be 40 counts per minute. And the reason for that is because there are 1/2 the number of radioactive isotopes present. The other 1/2 have decayed. We go on by another half-life and we find the decay rate is 20 counts per minute. We go on again and it's 10 counts per minute. And so in the same way as we measured the number of radioactive isotopes in the first lesson, in this lesson we're measuring the radioactive count rate, and we see we get the same kind of result. We find that the count rate drops by 1/2 in the same period of time called the half-life. So we can write another very similar definition for the half-life. This time we can say the half-life is the time taken for the count rate to drop by 1/2. Now then, one very important point that we're going to mention here is this, that when we do any experiment measuring the radioactivity of a particular source, we should always take into account what is called the background radiation. This means that there will be a level of radiation present which has nothing to do with the actual radioactive source that you're measuring. It's simply due to the background radiation. That might be some problem with other materials present in the lab, or it could be due to the rocks on which the laboratory is built, or it might be some other source of radiation coming from outer space. All of these things add up to form this background radiation, and so we must take that into account. So in fact, what happens when we take our measurements of this sample is that we find that the count rate looks something like this. Okay, so we're writing here this time, this is the count rate, this is counts per minute, and that we start off with a count rate of 90, and then after one half-life that's dropped down to 50, after another half-life to 30, after another to 20, after another to 15, after that to 12.5, and what we notice is that the radioactive decay curve is approaching a limit below which it will not drop, and this limit is due to the presence of the background radiation. Okay, and you can clearly see that in this case our graph is approaching a count rate of 10, and this is due to the presence of background radiation. And so this background radiation problem is always encountered in questions or exam questions on measuring radioactive decay. So the first thing we need to do before we try to measure the half-life of our sample is we need to take into account this background radiation level here. So what we've got to do is we've got to reduce all of our measurements by the value of the background radiation, which in this case is 10 counts per minute. So let's do that. We drop down from 90 to 80. These then are the actual values of our sample. So 50 will drop down to 40, drop down to 20, 30 to 20, 20 to 10, 15 to 5, 12.5 to 2.5, etc. And well, you might be asked to replot the curve. Okay, like that. So we do that, we replot the curve, and in doing so we've taken into account this 10 counts per minute background radiation figure. Okay, we can now calculate the half-life. So we ask ourselves, how long does it take for the count rate produced by our sample to drop by a half? We see that the initial value is 80, so we know that half of 80 is 40. We move down to 40 and we draw a line across there, and that tells us the value of our half-life.